All right, so this video is about the properties of a polynomial. And as you know, a polynomial is smooth and continuous. So as you graph this, it'll always be a nice, smooth, continuous graph. And it makes these shapes. Remember, we have the behavior we just talked about. This is a downward behavior. So we already know this has to be a negative x to an even. And this has to be an x to an odd based on its end behavior, right? So there's other stuff that happens. So the x values that make a function 0 are called our zeros. So that would be these numbers right here. When the graph hits the x-axis, those gives us our zeros. So that's our red dot. The turning points, this is when our function turns. So it's going from increase to decrease to increase to decrease. So when we have that change from increase to decrease, and that's decrease too, so we can save a little time through here, and that's increase right there. Those points right here, these are our turning points, and we'll put them in green. Those are our turning points because they change from increase to decrease. Now, the max number of possible, this is why we need those definitions, the max number of possible x-intercepts is the degree of the polynomial. So right here we have 4 x-intercepts. So we know our degree of our polynomial here must be bigger than 4. We know this is an x to the 4th, or an x to the 6th, or an x to the 8th, but we know it's definitely not an x squared because our number of intercepts are 4. We have 4 zeros. But we also know it's negative because it's got the downward bin behavior. So it tells us a lot about those problems. So now, max number of possible turning points. This is our degree of our polynomial minus 1. So we know it's 1, 2, 3, 4. We have 3. See how it's 1 less? So these will always be 1 less than the number of zeros, because if you cross the x-axis, and then you cross it again, and then you cross it again, and then you cross it. In order to do that, to cross it and cross it, you have to have a turning point. And then to cross and then come back, you have to have a turning point. And then to cross and come back, you have... So these turning points you see appear between the intercepts, because if there's an intercept here, you have to turn back around to get to it. I have to turn around to get to it. I have to turn around to get to it. So that's why they call them turning points. Okay, so what we're going to do here is we're going to label the zeros, give the locations of the turning points, determine if the degree is odd, even, or if the function has a negative leading coefficient. So we're going to talk about the whole thing just looking at the graph. We're reversing it. So we're going to label it, label the zeros. And so our zeros here would be, we're just going to do a rough one, 1, 2, 3, 4, 5, 6, 7 and a half. So negative 7.5. Let's do that in red so it matches. This would be negative 2.5. This would be, I don't know, 1.9. And that one looks like it's dead on. So 1, 2, 3, 4, 5, 6, 7. 7. So your zeros would be negative 7.5, negative 2.5, 1.9, and 7. And since we have 4 zeros, we know this is probably an x to the 4th, or an x to the 6th, or an x to the 8th. So we're just going to say it's about x to the 4th, but we know it's got to be somewhere like that or more, right? All right. And then we now need to locate and determine, where is it? Locate the turning points as well. So right here is our turning point. So that's 1, 2, 3, 4 at 4, 1, 2, 3, 4, 5, 6. 4, 6 is a turning point. And then 1, 2, 3, 4, 5. So 5, 7, that's a turning point. And then this one is about negative 1 point, I don't know, negative 0.2. Comma 1, 2, 3, 4, 5, negative 5. So our turning points are 5, 7, negative, here I'll write them downwards, negative 0.2, comma negative 5, and 4, 6. And from those, just like we've done before, we already know that it's going to increase to that point. So our intervals of increase would be negative infinity to 5, and from negative 0.2 to 4, and so on. And we can use Desmos to pop those things out. Okay, now determine if the degree is odd or even, or if the function has a negative coefficient. So we've already decided that it's even because it's our end behavior. So we know it's got to be x to the even, right? And it has to have a negative leading coefficient. So this is all you're going to be asked on these problems: to find the turning points, to find the zeros, and to decide what the degree is, whether it's even or odd, and if there's a negative leading coefficient. So let me have you try this one now. I want you to label all the turning points and all the zeros, and then tell me what the degree is and if it's got a negative leading coefficient. So hit pause now and give that a shot. So you should have had this. These are our turning points. These are the zeros. And it would have to be a positive odd. And so we know there's 1, 2, 3, right? And so according to that, the max number of intercepts is the degree of the polynomial. So we know this is at least a degree 3, which just makes it odd. But we know it's not an x, obviously. But it's x to the odd. So 3, 5, 7, 9, any of those would give us this. Because again, it's the max number. Max number meaning there can be more. So this could also be an x to the 7. Could look exactly the same way. Okay. So now what I want you to do, and what we're going to do, is actually here's some information, and we're going to draw a polynomial given this function. So it could be any polynomial that we want, but we have zeros that are 2. It's got an even degree, and it's got a positive leading coefficient. So we just want to draw that one that has 2 zeros. So it has to go through 1, 2, 3, 4, and 5. Those are our zeros. It's got an even degree with a positive leading coefficient. So we know it looks like this. So its end behavior is this. So what that means is from this point, it does this, and from this point, it does this. This is what it has to do. If you follow it down, coming in, so you always think from left to right, as we're coming in, it's going to cross here, and then it's going to cross here again. So coming from this point, it has to go off to infinity, and from this point, it has to go off to infinity. Because if it didn't, and say that you had it do this, that is not a negative leading coefficient, because it cannot. That is not an even function. If it does this, in order for it to be even, it has to do what? It has to end like that for an even. And what did that just create? Another 0. So that's not going to be possible. So wherever your zeros are, the outer 2 are where our end behavior continues from. So the end behavior starts here. Behavior starts with an H. Behavior starts at the outer endpoints, outer zeros. Got it? And then in the middle, you just do whatever you want. So you can have it come down and do a little loop here, or you can just be boring and do that. But yeah, that would be a function right there, the most basic. You could even have it touch and come back up, and then touch again and go back up. But as long as your only zeros are these, and the end behavior is that, you've plotted the function. So I want you to create one now from -10, 0, and 10. Those are your zeros. It's got an odd degree with a negative coefficient. So start by plotting these, and then use the end behavior, and then connect the dots. So hit pause now and give it a shot. So everyone should have had this. We have -10, 0, and 10. It's an odd degree with a negative coefficient. So this is our situation. This is our end behavior. So this is what everyone should have this. And then from here, it's just connecting. And now mind you can't do this because that increases the number of zeros, which we don't have. So you can only cross at that point. So you can do this. That's a very creative one. But I guarantee most of you just did this, the most basic, which is fine. That's all you need. So there you go. So there's 2 things going on these graphs. We have zeros, we have turning points, and then we get to use our end behavior from before. So it's 3 things actually. Thank you.